So we can see now that if we count the probability of event A as dependent on the event B, the result is different from what we get if we view the event A as an independent one. Hence, gender and attitude towards psychotherapy are dependent on each other. But since the difference between the resulting probabilities is quite low, we conclude that the degree of dependency is not very high. We often need further rules for considering two events, A and B, at the same time. If we ask for the probability that either the event A or the event B occurs, we should use the so-called addition theorem. If we ask for the probability that event A as well as event B occurs, we should use the so-called multiplication theorem. If A and B cannot occur simultaneously, we say they are mutually exclusive events. Then the second formula returns 0, and the first formula is therefore simplified. If A and B are independent, the multiplication is counted in a simplified way. So let us take the events A and B from our example and implement the formulas given above for addition theorem and for multiplication theorem. First, we count the probability of being a woman and having a positive attitude to visit a psychotherapist. Secondly, we count probability of being either a woman or having a positive attitude to a psychotherapist, to visiting a psychotherapist. In order to use the notion of probability in relation to a character, we interpret a character in such a way that the occurrence of each of its measurement values is considered to be a random event. That is, we model each character with a so-called random variable x. A variable that takes certain values x, observations or outcomes in a sample. In our case, a certain outcome of a random variable does not depend deterministically and exclusively on any mathematical function, but mainly on chance. Analogous to characters, we distinguish between discrete random variables and continuous random variables. Discrete random variables take any of a specified, finite, or countable list of values. In contrast, continuous random variables take any numerical value in an interval or collection of intervals. A probability distribution of each random variable defined within a sample space S is a mathematical description of the probabilities of events, subsets of the sample space. The sample space is the set of all possible outcomes of a random phenomenon being observed. It may be any set, a set of real numbers, a set of vectors, a set of arbitrary non-numerical values, etc. For example, the sample space of a coin flip would be heads and tails. In case of a discrete random variable, the distribution can be characterized by the probability function that gives the probability of the occurrence of each measurement value. Or in other words, probability mass function is a function that gives the probability that a discrete random variable is exactly equal to some value. If we consider a value x of a random variable to be an event A in a sample space S, then we can count the probability of the occurrence of this event on a sample space by means of the probability mass function, considering that for every element in the sample space S, all the probabilities must be positive. All probabilities are greater than or equal to 0. If you add up the probabilities for all of the possible x values, in the sample space S, then the sum must be equal to 1. Individual probability is found by the sum of probabilities of x values in the event A. Any event in the distribution has probability of happening between 0 and 1. Let us take a look at the example. A fair coin is tossed twice. Let x be defined as a number of heads shown. First, find the range of x and its probability mass function. Here is the solution. We have a sample space as a set of possible outcomes, head, head, tail, tail, head, tail, tail, head. And the number of heads can be 0, 1, or 2. So the range is 0, 1, 2. The probability mass function is count for every possible outcome. The probability of getting no head is 1 in 4. The probability of getting 1 head is 1 in 2. The probability of getting 2 heads is 1 in 4. In essence, with probability mass function, we use the same attitude as we used by counting the probabilities of the events. We divide a number of realization options of the value x by the number of all realization options of a random variable in a sample space. Getting back to the 2 dice example, the probability of 1, 2, 3, and 3 combinations is 3 in 36 or 1 in 12, because we have 3 possible events when the value of interest might occur, and each of the events has the probability of 1 in 36. Frequently, we deal with continuous characters and model them, of course, with a continuous random variable. The number of measurement value is theoretically infinite, even if, due to the given measuring method and precision of the instruments, this will not be apparent in practice. When a random variable takes values from a continuum, then typically any individual outcome has probability 0, and only events that include infinitely many outcomes, such as intervals, can have positive probability. For example, consider measuring the weight of a piece of ham in the supermarket and assume the scale has many digits of precision. The probability that weight is exactly 500 grams is 0, and it will most likely have some non-zero decimal digits. In order to count probabilities for a continuous random variable, we use the probability density function. Probability density function is a function used to specify the probability of the random variable falling within a particular range of values. Here is an example. During the day, a clock at random stops once at any time, and we have to count the probability that the clock stops between 2 p.m. and 2:45 p.m. So the probability that clock stops at any hour is 1 in 24, and we multiply this value with the difference between upper limit 1445 and the lower limit 1400. And this is how we get the probability. Here is a graphic representation of a probability density function, which shows the probability that the random variable is no larger than a given value a, and a graphic representation of a probability mass function that shows the probability of a fair die to get one of 6 possible values.